Folegot. Please.
Thank you very much. First of all, I'd like to thank the organizers for inviting me today. You're right, my talk is going to be very, very relaxing compared to the previous ones. I promise. I'm going to talk about underwater noise under ice conditions. And the talk is going to go to describe first the ice chorus and then explain what's going on in this chorus nowadays and what the future challenge we'll have to face. Just maybe one word about Quiet Oceans. Quiet Oceans is a French SME created 7 years ago to deal with this emerging topic of underwater, the environmental component of the underwater noise. I'm going to explain this later. So today, basically 3 parts in my talk. First, I will describe the sound chorus, so all the mixing of sounds you have in general in the ocean and then in particular under ice conditions. Then explain what are the effects of sound on the marine fauna and what are the future challenges in icy conditions and especially in the Arctic linked to this underwater noise. So when you go to the ocean, actually you already have a lot of things going on in the ocean, and most of the things going on in the oceans are producing sounds, and the sounds will propagate into the medium. You will have first, you can have wind, and rain. So rain will produce sound. Lightning would produce sound. Then you have inhabitants in the ocean, like big whales or smaller whales and fish that also produce sound. And then you have some human activities here on the surface or sometimes below the surface that are also producing sounds. And all that is mixing together to form what we call the underwater noise chorus. So to be more theoretical, if we can, we have 3 families of sounds. The first one is what we call geophony, which is the sound, the natural sound produced by a number of things, by the earthquakes, for example, underwater, the surface waves driven by wind. Waves will generate bubbles, and the bubbles will generate sound that will then propagate into the medium. Rainfall as well, as the water drops the surface, and ice. Then the second family is about the biophony, which is all the sounds produced by the marine fauna. You'll find the marine mammals, the invertebrates, the benthos, and fish. And then the human comes on top of that with his activities and, for example, sea bottom mapping, all the eco-sounders and tomography experiments, seismic survey, offshore construction activities, and shipping. And all that is mixing. So here's a graph that explains a little bit how it's distributed, how the sound is distributed as a function of frequency here. That goes from 1 Hertz to 100,000 Hertz in this graph. And here an idea of the typical sound levels you will find underwater. And you can see that each line here is a different type of sound. The red ones here is about shipping noise. That is actually using this band from 10 Hertz to 1 kilohertz, roughly. And the blue lines here are natural noise driven by the surface waves. As you can see, as the sea state increase, the level will increase from a few hundred hertz to a few tenths of kilohertz. Then you have some natural noise here, also very high intensity, which is due to the cracking of the earth. And here I superpose the same type of graph for ice. These three blue curves is for the Arctic and Antarctic, while the green one is ice. Well, the noise you can find in fjord when it's covered with ice. You can see that you basically have a shift in frequencies if you are in a smaller area in the fjord, and that's because it's more reverberant. So the noise is just bouncing in this place, and you have more constraints. The ice is more constrained as in open waters, and that explains why it's shifting towards the higher frequencies. And you can see that the levels are, when you are under ice conditions, it's very likely that the noise produced by the ice will dominate the other type of sounds. It's because you have a lot of energy involved. If you look at here, some experiment done some time ago. Here you have pack ice, and they made some measurements of noise when you go from open waters to pack ice conditions. Interestingly, at the edge of the pack ice, you have a peak in the noise levels. It's because that's where basically you will have the most dynamics in your ice. And so you have variability. The noise generated by the ice will create quite a spatial variability here. Then you have some events in icy conditions, like here calving. And so you have different type of calving. Here, as you can see, the graph from top to bottom, or bottom to the top of the sea surface, it would generate different type of sound. Here, this three graphs is time and frequency from 10 hertz to 10 kilohertz. And you can see that according to the event, the type of noise will spread at different times and will be at different frequencies. And actually, for each event, you'll have a different sound. So that's a very, very large diversity of sounds generated by ice. You have ice quakes, cracks, cracking of the ice, iceberg, calving of icebergs here, generation of icebergs that can last very long time until it really forms. It starts generating noise before it really calves. Then when the ice gets compressed, then you have this kind of I don't really know the name in English, but this kind of long, almost monochromatic sounds. That can last also quite a long time, because the process of compressing ice can last a long time. This is also some event of when the pack ice is moving like this. And this is when an iceberg is melting, it generates bubbles underwater, and these bubbles generate sound. So each time you generate bubbles, you will create some noise. So a very large diversity in terms of, so that there are almost all transient sounds, but it goes from a few milliseconds or tens of milliseconds to minutes of sounds, of transient sounds. And the frequency can change drastically as well. So all these sounds are driven by a number of external parameters. The formation of pack ice, it's driven by the temperature. When the temperature drops, ice form, and then it's the temperature that will which is the driver for generating sound. When the pack ice is moving, it's forced by wind and waves. Compression of pack ice, it's temperature. Calving, it's when the temperature increase, then you start to have the calving effects. And then the icebergs, when they clash together, generate noise as well, and that's driven by current, wind, and waves. When the iceberg drifts, that's mainly driven by swell and current, I should add, probably. And when it's melting, it's temperature. And here I've put an indication of the frequency band of all these sounds. So here is an interesting work, 2008, by Ross, on almost 1 year of observation. That's the status of the ice, and the type, so from September to June, and they have identified what is happening here on the ice, and they superposed to this. They did some passive acoustic recordings to listen to the biological noise, and they superposed here here for the beluga, when the beluga were present, and as a function of the state of the ice. This is for the beluga, and this is for the seals. You can see that looks like the beluga and the seals. They use the place. They are mutually exclusive. So to try to give a more synthetic view, I tried to make this kind of graph. Here you have time from December, March, June, August. Oops, sorry for the August. This is time here when you turn. Here is the type of ice you will find, which generate different type of sounds here. And this period of time here, it's ice-free. And here it becomes wind and waves driven noise. All right, no more ice driven noise. And because it's a free waters here, you start to have some anthropogenic activities like seismic surveys and shipping and cruising. But basically, the biological sounds will be present all the year through, but maybe not from the same species. So, why are we interested in this? It's a growing concern. The noise that is generated by the human activities is a growing concern, and regulation is emerging since 10, 20 years. It has started with some at the United Nations level, with some where noise were started to be mentioned as an issue in some conventions, international convention and agreements. And in Europe, the very first time we had underwater noise mentioned is in 2010 with the Marine Strategy Framework Directive, that clearly said that underwater noise is an indicator for a good environmental status of the ocean. And then from that, because noise was declared as an indicator for good environmental status, and because you had other directives in Europe dealing with the species and the habitat, then noise becomes a complete topic, actually, regulatory topic that is now converted into national regulations. So what the Marine Strategy Framework Directive says, it recognizes the adverse effect on the marine life of underwater sound. And it has defined two descriptors. The first one is about impulsive noise, and the recommendation is to build up a registry of impulsive noise made by human activities, like, for example, seismic surveys or piling activities. And the second descriptor is about the continuous noise, and has been defined two ways at looking at the continuous noise. So continuous noise is the chronicle noise, like shipping noise, for example. And it has been decided to look at specifically at 2/3 octaves, which is 63 hertz and 125 hertz, as an indicator for this chronicle noise, because that's where the rationale behind that was that in these two frequencies is where the most of the shipping noise is present. So what are the risks? There is an international consensus on the nature and the scale of the risks of underwater noise, man-made noise on marine life. And the scale of risk is this one. The arrow here describes if you go from loud noise to low noise. Okay, if you go away from the sound source, and I start from this end here, where if you are very far of a sound source, you won't be able to listen to that sound source. So you are in another type of sound. You're not exposed to this sound, and you are exposed to other type of sounds, which let's call it environmental noise. Then, if you go closer, you will start to be the sound. You can be exposed to the sound with no particular effect, as you are right now. Hopefully, when I'm talking, you can listen to me, but I hope there is no particular effect on what I'm saying. Then you have an area where when the background level is increasing, you have a zone of what we call masking. Masking, you all experience masking when, for example, not during the coffee break, but maybe when you go in a bar, there is a lot of people. And so first the bar is empty, and you can talk with your friend at a regular distance. And if now people entering the bar, the noise level in the bar increases, yeah, then you start to be able to have a discussion with your friend, you'll have to go closer. It's because it's more noisy, so your acoustic space is reducing. That's called masking, and that's very important for the marine fauna, because the marine fauna is using sounds. We are convinced that very large majority, actually every animal that is producing sound, it's producing sound for a purpose. It's for communicating so that they can reproduce, or it's for hunting. So sound, actually, if they produce sound, it's very important for them in their life. So masking is very important, because if you reduce the space, your acoustical space, you reduce the possibility to do stuff. Then when the noise is still increase, you can start to have behavioral reaction, meaning that it's annoying and the species will leave the area. And then here, these two last steps is when you start to have physical damage. Physical damage, temporary. That's like when you go to a disco, for example. When you exit the disco, sometimes you can still have some annoying noise, but the next morning everything should come all right again. So that's a temporary physical damage, which for us is okay. For the mammals that use sound, it's not okay. And then you have a zone of injury, where permanent injury, meaning that the cells are damaged forever. So there is an agreement, international agreement on all this scale of risks. And nowadays, there are an international agreement on the threshold to go from, on this threshold here, that goes from to when temporary damage starts and when permanent damage starts. So this is agreed. It doesn't mean that it's not going to change, because science is progressing on this. It's a very long-run science behind this. but at least so this paper here is giving the agreed thresholds. This is a 2016 version, but there was before that there was a 2007 version. So it's going to be updated probably every 10 years based on the new knowledge that comes from the science. And this is about fish. So this describes also these two thresholds for fish. And that's the first time we have an agreement on fish thresholds, and that's 2014. For the other thresholds, it's much more complicated, and science is not there yet, really. So we'll have to wait a bit more. So the way we do a risk assessment is this is the methodology and with the expected results, 3 phases, and that's the tools we use. Basically, first you have to do a baseline assessment, because when you have a project somewhere, there is already noise. It can be natural noise, it can be biological noise, it can be anthropogenic noise, it can be the 3 of them. It's usually, and very often, it's the 3 of them. So first thing you have to know if you are in a quiet area or in a busy area. And you also have to know what species are there in the area where you'll have your project. Then you take your project activities and you predict how much noise it's going to add to this chorus, to the initial chorus, to the baseline. And then you can evaluate with the threshold that are known. You can evaluate the risks and advise and define a strategy to either, if the risks are not acceptable, to reduce the risk, or to reduce the risk if needed. And then once the project starts and you have some risks to monitor or to control, then you will put in place a monitoring based on visual observation or measurements, acoustic measurements. So we have developed a tool to be able to implement this, which is a kind of prediction system, where we basically put together a number of information about what is going on the ocean as maritime activities. It can be shipping, but a seismic survey or whatever type of activity. Then we need to know, so that's our sound sources basically. Then we need to know how it's going to propagate. So we are connected to databases for the bathymetry, the sediment type. And we also have to describe the water column, because the sound will propagate according to the distribution in temperature and salinity and the surface roughness. And we are connected to operational oceanography services, Copernicus in particular, with Mercator Ocean, that gives us a prediction at any place, any time, prediction of the temperature and salinity and sea surface roughness. We'll have to also to do measurements to ground truth the modeling. We are going to use all this data to do modeling, and we need to have a ground truth. It's like for weather forecasting, you have weather stations, and then you implement modeling, and you use your weather stations to ground truth your results. So our job is basically to put this together. It's done in a system, and we call that operational ocean noise system. What we are able to do nowadays is to model the sound that comes from is generated by surface waves, and the sound from the maritime activities. Okay, so some other components are missing, but that's what we can do so far. Here's an example of live modeling, live mapping. It's the 125 octave, so as required by the Marine Strategy Framework Directive. In 2014, it's the sound pressure level, and that's for shipping. All the red dots here, you can see, are vessels that are cruising in the area. That's in France. I'm living here, in the northwest of France. And so you can see here that the sound that's spread around the vessels depends on the type of vessel. Each type of vessel will generate different source levels and different frequency bands. And it spreads differently according where they are because of the bathymetry or because of the environmental conditions. Okay, so that's noise, but it's difficult to do something with this because it's changing every 15 minutes. It's a different image, different information. So we had the approach we are proposing is to do a statistic of that. You run this for a day, for example, for months, and then at a given position, you will look at the statistic of the noise at this location for your period of time. And that's what we've done, for example, in a European project called BIAS, which was a Life Plus project from the EU, where we mapped the whole Baltic Sea. So we had 40 sensors, acoustic sensors, deployed for 1 year in the area, and to ground truth the modeling. And then what we did is for each image is 1 month statistics of the shipping noise and natural and noise from surface waves. Right? And what you can see is that it's variable according to the months, but not everything is variable here. You can see that the noise generated by here you have the main, for example, the main shipping lane here. And there is no seasonal variability in this. I mean, the shipping is going on same January, June, whatever. It's always more or less the same density. But some other activities are depending on the season. And the natural noise, actually, what you can see the background here, you can see that in summer it becomes much, much quieter, just because there is less wind. So that's the natural component, actually, that is doing this seasonal change. You can also have some other changes linked to fishing, for example, that may occur in some places for 3 months and then disappear or change place. That's the same, but for another frequency. The other one was at, what, 63? It's 125 hertz, as required by the MSFD. But we also looked at higher frequency because that has some interest for some species that are using higher frequencies. And so we did exactly the same exercise here. You can see that clearly the natural noise is much more dominant at these higher frequencies, which makes sense because shipping is producing sound in the more lower frequencies. So what we did then is to look at how much does the shipping and the fishing activities add to the natural noise. Okay. And so we look at the median exceedance of the shipping noise above the natural noise, okay, on a statistic for 1 month. I think this is August. And what you can see is that the white places is where half of the time the natural noise is dominating. And where it's colored, it means that places where it's the anthropogenic noise that is dominating half of the time, and it gives an indication on how many dB it adds to the natural noise. So that starts to be interesting to evaluate risk, if there are some risk, and where, and to understand. So again, about masking. As explained, masking is a reduction in communication detection range due to a raise of the ambient noise, the background noise. Let's take the example of codfish. Codfish is, cod are producing sounds, very low frequency. The male and the female, they do not live together, usually. I don't remember which one is the male and which one is the female. I should know, but let's say this is a female, is living very close to the sea bottom, and the males are living on above the sea bottom, maybe 20 meters above. All right. But at one point they have to meet to be able to reproduce, right? And to do so, the female will send a sound, and the sound will be received by the male, so that they know it's time. Now, if you increase the background levels because of other activities, this distance here, well, the level received from this signal will be received. It will become more and more difficult to receive this signal. And this distance may be reduced. The distance where you can receive this signal can be reduced, and then maybe the reproduction will not occur. So this kind of things is long-term effect. Very difficult then to quantify exactly what is going to be the impact for next month or next year or even next 10 years. But we know that's an effect. So how far are we? We did that exercise we put in place a model that is estimating the reduction range, how much the communication range is reduced. So that's reduced by the fact that you have shipping. Okay, so we started from the exceedance map I just showed before on how much the shipping is adding to the natural noise, and then we look. Okay, we have increased that many dBs. What's the consequence on the reduction of the communication range? And so again, you find the white places where it's natural noise is dominating, so we say there is no consequences. And then where it's colored, it means that the communication range is reduced by a factor of this scale. So here the yellow is about 10. So you go from 20 meters to 2 meters. Right? And when it's red, it's divided by 50. So it becomes just nothing, right? So back in the ice, sorry, that was maybe a bit long, but what is happening in the Arctic in particular? The consequences of so the climate is changing, and that opens new routes shipping routes across the Arctic, and it also opens space and period of time where you can do other activities like seismic surveys or cruising. So if we put this graph back, it means that this period will increase, and it's likely that these activities will spread more time over the year. And then this cycle here will also change because you have more non-ice covered places. So this will more compact, so we change a little bit the seasonal dynamics of the natural chorus from ice. And the big challenge now is to try to assess or try to estimate what is going to be the impact for the marine fauna that are used to live in this cycle and these kind of conditions. So our challenge then is try to add an ice component to our noise map. For now, we deal with the waves, surface waves, and maritime activities. So if we want to deal with what is happening in the Arctic, we'll have to add an ice component, which is not done yet. So we'll have to deal with the propagation of the sounds under ice. And ice will influence the propagation because it adds some, the boundary between the water and the ice is going to influence the propagation. Each time the sound bounce on this interface, it will interact with this roughness. Here is an example distance from a sound source and the loss in the loss of the sound intensity without ice in blue and with ice in red. You can see that because of the roughness of the ice, you add dispersion, you add and absorption and all that, and so you propagate less well. Of course, it's very challenging to model. Well, we know how to model acoustic propagation. That's the acoustic propagation with a flat surface, right? You have a sound source here, and in red, that's how the sound spreads in the ocean as a function of depth and range. Now, if you add here a profile, this is the ice profile at the interface. that's how the propagation will become. It's drastically different, all right? But what is difficult, it's not to model this, it's to get this information, especially when you start to deal with mapping, meaning some kind of global situations. It's very difficult. The uncertainty actually is more in this. Another type of difficulty is to identify the sound source. If we want to add a natural ice chorus into our maps, as we do for the waves, we'll have to know the different sound sources from ice, and as I explained at the beginning of the talk, there is such a large variability and differences. It's very, very challenging. Probably a statistical approach would be a solution. But okay, so just to finish, the ocean is, there is a chorus of sounds in the ocean, and ice is contributing to this chorus in a very diverse and diverse manners, since every type of ice will generate a different type of sound. That can be very high intensity sounds. The sounds will propagate at very long ranges, especially if it's low frequency, which is for ice, it's the case. And that will, all these ice sounds already introduce masking effects. But masking effects can also occur from other sources. And we now know, and it's now regulated, that the sound introduced by human activities can impact the marine fauna. So if we want to go further in dealing with this challenge in ice conditions, we would be very interested to work on this. We haven't started yet, but maybe here in the assembly there are some people that we could team up. So this is a call for collaborations and maybe to put some proposal together. The idea, there are three different ways I'm going to suggest today, is to, by recording the sounds from ice, you will be able to monitor the different type of ice that is present in your environment, and that maybe could help you to do your modeling and to describe and to do your work in understanding the interaction between ice and fluid. So using the underwater acoustic to monitor the ice, some people already started to do this, obviously. Then how to include the ice component into sound maps. This is very challenging. And then once we have this, or when we start to tackle this, and how to predict the risk in this kind of environment, challenging environment. And that's it for today. Thank you very much.
Thank you for interesting talk. Questions, please. Okay.
Yeah, do you have a sample of this hydrophone chorus?
Sorry, what?
We can hear this chorus.
Oh, no, sorry, I don't. Actually, I didn't know if we were equipped with some loudspeakers, but you can find some here. A few of them, if you go there. I have a reference, a website somewhere. Okay, go there. You'll find some interesting sounds.
More questions? Oh, please.
Then it's, yeah, okay, sorry.
I guess just really simple question. How much of the noise that is in the ocean is man-made? Like what percentage of it is?
Depends where you are. It really depends. Look at this. Let's have a look just in the Baltic Sea, for example.
The majority of it.
Depends where you are. It depends when you are. And it depends on what frequency you're looking for.
But if I interpreted that picture, I'd say only on the shipping lanes is it that we're going to have man-made noise dominating over ones that were always there for the last millions of years.
Yeah. But that's on some other places, like here, for example, this can be fishing,
Okay, yeah.
for example, or everything is mixing and depends on when and where, and that makes the thing difficult. So there is no single answer to this. Even sometimes you can have some people saying, well, the noise from human-made noise is increasing by 3 dB every decade. I can find counter examples where it's not the case, and well, I mean, tons of counter examples. So that's too simple.
Please.
Thank you for a very interesting presentation. I have one question related to the picture on the wall. I mean, is there a difference in winter when the northern Baltic Sea is ice covered?
Yes.
Is there a difference in noise levels from shipping during winter time compared to the summertime?
Yeah. We were kind of lucky. Since 2014, there was a little ice coverage. So this region actually is concerned with ice. But in 2014, there was not that much, as far as I understand. So here, we know here that we are not very good in the modeling, in the mapping. But one consequence is that the traffic here becomes more seasonal because of the ice coverage. So the first change is that when it's ice covered, you have less traffic than when it's open waters. So that's the first signal. But then for modeling the contribution of the ice noise into this basin, for example, here, so far it's not done. That's something we would like to do, but as I said, long way to go.
I have a question. It would be great to have a list of sources of sound caused by ice, like cracking, collision,
Yes.
friction.
Yes.
Do you have that list? Or
Yeah, more or less, yes, I do.
Yeah. Could you say
I can
something?
give you your business card and I'll send you something.
Okay.
Okay.
So it's not open. List is not open. Oh,
Oh, it is.
it's
It
too
is.
long.
Or I'll send it to an organizer. I don't know.
Thank you.
Okay. Yeah.
It's that's the first part I said about the chorus was more a bibliographic overview. So it's not.
Is there any ambition to use these studies to sort of inform industrial policies?
Yes.
Very nice.
It's meant. This tool here is meant for management. Well, not only, but it's also meant for management because, well, that's what part of our business is to work with industry on estimating the risks of their project, and so we use this to estimate it to do typically. If I have if my customer have a project on here somewhere in the Baltic Sea in August, I will pick up the August map, and then I will add to this. So this is my baseline because this is the noise that exists already. Then I will add a sound source or multiple sound sources depending on the project, what it is. If it's an offshore wind farm, for example, and they are piling, I will add a piling somewhere at a realistic place, well, based on the project. And then I will do this calculation, but looking at now my baseline is this, and my additional noise is the project noise. And that gives me what we call the footprint of the activity. And from that's the material we use then to estimate, is it risky, not, where, everywhere, yes, no. And then we superpose to this the knowledge we have about what species are there and when and to do what.
So you could even affect the activities, saying that this will be a bad time to do.
Exactly. That's the kind of recommendation and discussion that we have to design the project. Yeah.
Last question. You.
And to design the monitoring program that comes after, that will go with the project.
Actually, just a short comment and a quick question regarding the sound, just to have a flavor for everyone. I actually have a sample from an earthquake with a higher frequency. So it's a bit freaky.
Okay, yeah, good, great. Great time.
Right. My question is regarding the simulations. Do you consider gravity also, or just pure acoustics?
Pure acoustics. And from what I saw this morning, I think I will stay there. No, I mean, no, yeah, purely acoustics.
Okay, thank you.